Hey guys, Mr. Betts here. I want to continue our conversation about limits by connecting them to something we should already be a little bit familiar with, and that is vertical asymptotes. So let's start with just some examples of functions here, and all three of these functions are going to have a vertical asymptote. And I want to talk about why using some pre-calculus ideas and then connect that to limits and how we can connect that to calculus. So I'm going to focus first on just this f function right here, and I'm going to try to get an idea of what this graph looks like by plotting some points. So I'm going to start by just choosing some x values, and I'm not going to be real rigorous with this, but I want to pick some specific x values that are going to be close to a point here where we know the function is going to be undefined. We know x is not going to be in our domain of f here, but I want to pick some points that are close to x equals 1 and see what happens. So if I pick a point like 1.1, then the value of f of x is going to be 1 over 0.1, which is going to be 1 divided by 1/10 is going to be 10. If I pick a number like 1.01, then we're going to have 1 over 1/100th, so we get 100. 1.001 is going to be 1 over 1,000th when we subtract the 1, and that gives us 1,000. You probably see a pattern happening here, so I'll do one more here, 1.001. So 1 and 1/10,000th is going to give us 10,000. And so what's happening here is I pick values closer and closer to x equals 1, and we're getting bigger and bigger and bigger numbers. Now, the idea of what we're doing here with our x values is the same thing we did with limits. So what we're looking at here is essentially what's the limit as x is approaching 1, and specifically in this problem, I'm approaching 1 from the right of this function f of x. Well, for this limit to exist, these values that we're getting here should be approaching some particular value. And we notice here that they're not approaching some particular value, they're just getting bigger and bigger and bigger. And it turns out that I can make this number in this column as big as I want by picking a number over here that's as close to 1 as I want. So this is getting straight to the definition of a limit. If I can get something that I want in this column by picking something as close to a value as I want in the x column, that's exactly what a limit means. So the difference here is we're not approaching some particular constant. We're not approaching some number, but we're getting unbounded numbers. So it gets bigger and bigger and bigger. Well, that idea in math of getting bigger and bigger and bigger and not being bounded is infinity. So we can say that this limit here as x approaches 1 from the right is infinite. Now, I'm getting a little ahead of myself here. If we just think of what the graph is going to look like and we're plotting points, what ends up happening here is we get a vertical asymptote. So as we get closer and closer to x equals 1, we're going to be getting values that are getting bigger and bigger and bigger. And so we're getting a graph that's going to look like that. So all three of these functions are going to have a vertical asymptote. And more specifically, they're all going to have a vertical asymptote at x equals 1 because we're dividing by that x minus 1 in the denominator. I do want to point out that on the last one here, we don't get a vertical asymptote at x equals -1. And the reason is if I pick values that are close to x equals -1 here for h of x, let's say -1.1, on top, we get -0.1 over -2.1 times -0.1. And what's going to happen with any number that I pick, I'm going to get the same thing on the top as I get on the bottom here with the x plus 1 factor. And so what that means is these are essentially going to be canceling each other out. So no matter how close to -1 I get, this is going to cancel this out, and that might sound familiar, and that's going to give us a hole or a removable discontinuity. So let's look at the graphs of these functions here, and let's kind of talk about how we can tie it together with vertical asymptotes. So each one of them does have a vertical asymptote at x equals 1, like I said. And as we expected, we're getting values of the function that are getting really big as we approach that vertical asymptote from the right. in that first function, um, as we approach from the left, which I didn't do, but you could do, we're getting negative values. And the reason is if I put a number in for x that's smaller than 1, we get a negative number in the bottom. So it's going to be 1 divided by a number that's really close to 0 but negative. Positive divided by negative gives us a negative. So we can describe this behavior with limits. So I already got to this in the when we were looking at the table of values. But if we're approaching this vertical asymptote from the right, so along the x-axis, we're moving along this curve and getting closer and closer and closer to 1, then that is looking at this limit right here. And I'm just going to put f of x. We could also put in here 1 over x minus 1. Those are the same thing. And again, since it's not approaching some constant, this limit technically does not exist. But we can be a little bit more specific. Instead of saying it doesn't exist, we can say that that is an infinite limit. And that's just giving us a little bit more of a description of what's going on with the picture of the graph. So as we approach 1 from the right on the x-axis, then the y values are getting really, really, really big. On the other hand, if we look at the limit as x approaches 1 from the left of f of x, the numbers are going to be approaching negative infinity, a really big negative number. So we can say that even though this limit doesn't exist, we can say the limit is positive infinity or negative infinity to describe the behavior of the graph around that vertical asymptote. Now, this one over here, the graph of g, if we look at both of the one-sided limits, they're both going to be positive infinity. And the reason they're both positive is because whatever we get down here for the x minus 1, when we square it, it's going to be positive. So we have a positive divided by a positive. And this is kind of a tricky idea, but since both of the one-sided limits are both going to positive infinity, still the two-sided limit does not exist, just like I said with the f of x function. However, we can say the limit as x approaches 1 of g of x is equal to positive infinity. So again, technically this limit does not exist, but by saying the limit is infinite, it tells us that as we get closer and closer to 1 on the graph of g, we're going to get really big values for g. And since I'm not saying whether it's from the right side or from the left side, then that means that it's happening on both sides. Okay. H of x is actually the same function as f of x. I mentioned this earlier, but because we have the same factor in the top and the bottom, those two functions are identical except where x is equal to -1. I put this problem in here because I want to make sure we understand that usually we're going to get vertical asymptotes when the denominator is equal to 0. However, if we have the denominator equal to 0, but that factor can cancel with a factor in the numerator, then what we end up with is a hole in the graph. Now, we could look at a bunch of different situations here. We could say, okay, what happens if it's x squared or x plus 1 quantity squared? So one of those factors is going to cancel with the factor in the top, and then we would end up with a vertical asymptote in the denominator because the other factor does not. But in general, if we get 0 in the denominator, we're going to have a vertical asymptote as long as the numerator is not also 0 at that same point. So I already did this here, but we can connect the behavior of these functions then to the limits that describe what's going on by using positive and negative infinity in our limits.